draw out the pressure volume loop. I'm going to just start out something like this. And it's really easy to try to draw a pressure volume loop from scratch. That's one of the reasons I love about it. One of the things I love about it, rather. Got pressure on this side. And we're going to do it in millimeters of mercury, which is pretty typical for us, right? We've got 0 to 100. And let's just make this 120 up here. And this can be 50. And on the volume side, let's make this 100 over here. That makes this about 50. And I'll make this about 125, right? And I like to start out with kind of low pressure and high volume. That's the, I mean, you can start out anywhere in the loop, really, right? But I just like to always start out right here with a blue dot. And that's the point where the heart, the left ventricle specifically in the heart, is full of blood. And it's going to start squeezing, right? It's going to start contracting. So pressure is going to go straight up. And it's going to keep rising, rising, rising to about, let's say, here. And I hope that was a straight line. It's about around 80 or so. And then the blood starts getting into the aorta, right? Because the aortic valve flips open at that point. And so it starts losing volume because the blood volume is actually heading into the aorta. And then the volume continues to fall and the pressure begins to fall. And so it looks something like that. And that blue line that I drew so far, that is systole, right? That's systole. So that's the part where the muscle is contracting, or the heart muscle is contracting. And then you have the next part of the pressure volume loop where now you have relaxation. So you have a fall in pressure to about there, right? And then you have a continued decrease, right? It continues to go down, let's say, to about there. And this is now where blood is entering the left ventricle, which is why I'm showing it going up in volume. And you finish your loop something like that. So this is your pressure volume loop. Now I'm going to zoom in on, let's say, a heart cell, just to kind of point out what's going on at the heart cell level. And remember, heart cells are often branched, so I'm just going to draw it that way. And let's show some actin and myosin. Of course, I'm kind of exaggerating what it looks like, just to kind of make the point. But you might have something like this, right? Lots of actin and myosin inside of these cells. And remember, these cells, now I'm just kind of reviewing with you, have a nucleus here, and maybe a second nucleus there. But they're full of actin and myosin. It doesn't look exactly the way I drew it, but I just want to remind you that there is a lot of protein inside those cells. And the thing that these cells are waiting for is calcium, right? The moment calcium enters these cells, then they can contract. And if they contract, then you basically have this part occurring. And in fact, also this part occurring, right? This is all contraction. So all this contraction is happening with the assumption that calcium is coming inside of those cells. So what if I decide to play a little trick and I basically somehow I vacuum up all the calcium and I don't let that calcium enter the cell? Well, what would happen? Well, you might have a loop, but the moment I start doing this, then you don't really have contraction anymore, right? So all of a sudden, at this point, I'm going to just kind of erase it, you don't allow any more contraction, so you wouldn't have this sharp increase in pressure. In fact, you wouldn't have any of this, right? If I could actually vacuum up all the calcium, you wouldn't have any of that systole really happening. You'd be basically kind of stuck in diastole. So you'd basically be stuck here, right? And this is, remember, this point we used to call end diastolic. End diastolic. So when you get to that end diastolic point, instead you'd be basically kind of stuck in limbo, right? Now, what if I took it one step further and I said, well, I'm just going to make a little space here by erasing all this. What if I now draw for you the heart? Let's draw the left ventricle out like that. And I'm not going to draw the left atrium, just the left ventricle, and I'm going to fill it in to look something like this, right? So you've got lots of blood inside of that chamber of the heart, right? It's full of blood. And let's say now that it's full of blood and it's not contracting, I got to do something with the left ventricle, and I decide to kind of continue my experiment. And I say, okay, I'm going to take an injection, and I'm going to inject this left ventricle full of blood. I'm going to put more blood in to the left ventricle. I'm going to put more blood in. You might be thinking, well, how in the world do you put more blood into something that is full? If it's full, right? So how can you put more blood in? Well, think of it like a balloon. You can have a full balloon, but if you put enough pressure, you can actually increase the volume, right? So in this case, it will take pressure. And, I'm not going to, candy coat this. This will take work. But if you're willing to do it, you could actually put more blood into a full ventricle. So let's extend this out. Let's say I put some extra volume in, right? Like that. Well, my pressure will go up a little bit. And my curve will look like this. Let's say I extend this out. It'll start looking like that. And I could actually do it again. I could put more volume in there. And this time it took actually a little bit more effort because it's getting harder and harder, not unlike a balloon, right? It's looking like that. And I could do it again. I could say, well, let me try one more time. And now it's getting even harder, right? Even harder to do this. So my curve is kind of looking a little bit more like this, more steep as time goes on. So on the one hand, I'm adding more volume. That's what all these V's are. But as I do that, the pressure is going up. That's what these P's are. So pressure and volume are, of course, related, right? And we could do the reverse. I could actually flip it around and say, well, hold on a second. Instead of adding blood, what if I decide to take blood away? What if I want to do something like this, where I actually pull blood away off of the heart, suck it back and take it and maybe throw it down the sink? Then what would happen? Well, let's say I start at the same end diastolic point, just to kind of make it nice and clear. Well, if I was to do that, if I was to take blood away, then my volume, of course, would go down. And if the volume goes down, the pressure goes down. And then I could do it again. I could take more volume away, and the pressure would go down. And actually, it would look pretty much the same as that chunk of our pressure volume loop. So you can actually see now, when we have our pressure volume loop, that's actually kind of showing you what it would look like to fill up the heart. And it makes perfect sense, right? As you change the volume, of course, the pressure will fall a little bit. If you take more volume away, the pressure will fall even more. But what if I kept doing it? What if I just kept extending this out and taking more volume off? Well, the pressure would go down a little bit. And I could do it again. I could take even more volume off. And I could end up with really no blood in my chamber. And I would have, of course, no pressure at that point. So you can actually connect these lines. You could say, okay, well, this is kind of what the curve might look like, right? Something like that. And of course, I would have to erase this little chunk because that was not related to passive filling, right? That was, remember, where the heart was still, or the left ventricle was still relaxing. And I could also just erase all this stuff to make our line more clear and easy to see. And so now you see, what you see emerging is a fantastic relationship, right? A pressure-volume relationship. And this pressure-volume relationship is assuming that the left ventricle muscles are relaxed, right? This is assuming that there's no contraction happening. So remember my first assumption, which was around getting rid of that calcium, if you can really fully relax these cells, if they're relaxed, and then you kind of passively fill them up with blood or take blood away, like I've done with my injection, my needle, then you develop this interesting pressure-volume curve. So this is a pressure-volume relationship. Pressure-volume relationship. And you might actually see all this kind of shortened down. Sometimes people don't have the time to say, well, it's the end diastolic pressure-volume relationship. They have, that's 5 long words. So instead they might just say, well, this is your EDPVR. You might see that, EDPVR. And, one final point I want to leave you with is, remember, anytime you see pressure divided by volume, that's really a slope of a line, right? So this could be the slope of the line right there, or you could have the slope of the line right there. So anytime you have P over V, that's just a slope. And that slope equals the elastance. Remember the concept of elastance. Elastance is just the slope of the line. So if you ever want to think about it differently, you could say, well, really the end diastolic pressure-volume relationship line is also telling you a little bit about the elastance of the left ventricle, when it's relaxed. So I'll leave you there, and you can think about this a little bit more on your own.